again to the third and last talk of the morning session. It's my pleasure to introduce Enno Lenzmann, University of Basel, who will speak about turbulence, but now in completely integrated PDEs and the Calogero-Moser derivative NLS.
Yes, thank you. Thank you, Mats, and also it's really a great pleasure and honor to be here and be able to give a talk. Yeah, so actually it's okay, you will see turbulence, so it's continuing. Also the Sobolev norms will grow actually, I will show, from above and below precise bounds. However, in of course, a setting which is much different from what you were talking about. Okay, so what's this about? So I will introduce or discuss what we call the Calogero-Moser derivative NLS. So it's an NLS, nonlinear Schrödinger equation, posed on the real line or on the torus, but this talk is specifically about the case when it's posed on the real line, so it's a really dispersive.
Is this Jürgen Moser or some other Moser?
It is Jürgen Moser. You will see a picture of him very soon. Okay, I will also somewhat explain more detailed way how this can work out. So it's a completely integrable PDE, we will see, in the sense of having Lux pair structure, and Hardy space will play an important role as well to formulate, for instance, this Lux structure. However, on the other hand, it will also be a mass critical equation where global well-posedness for large data is a hard thing, and so it's an interesting combination of two worlds. Like you have infinitely many conservation laws on the one hand, which fail to control in some sense large solutions, which will enable us, for instance, to really show that we can really construct what here is called turbulent solution in this way of this growth of Sobolev norms. So we will construct smooth solutions globally in time, which is already not trivial because these are large solutions, so the global in time existence is not taken for granted, and you will have precise understanding of the growth of the Sobolev norms as time tends to infinity. And I should say this is joint work with Patrick Gérard, and it's found on arXiv. Okay, so I will first now explain a little bit what the F is, what the nonlinearity is, and as I already indicated there, it's a nonlinearity which also contains the derivative of u. So it's something that is not just something which only depends on u. And here is a little answer to your question. So it starts with a paper, a really very influential paper from the 70s by Jürgen Moser on what's now called Calogero-Moser systems. It's something from classical mechanics. You have classical particles, they're moving on the real line, and they interact with this very specific but interesting repulsive interaction of 1 over the distance squared. So this is the setting, and this was previously studied by Calogero in the beginning 70s in the quantum mechanical context. So Calogero looked at the quantum mechanical many particle system with this kind of singular interaction, which in quantum mechanics is really singular. It's not locally integrable. It's one kind of serious point about the quantum mechanical case, but he found many like explicit things which you can think it's like an exactly solvable system. So Calogero conjectured that the relevant classical system is maybe completely integrable. So Moser's idea then was very nice because he used Lux pairs to show that this system this classical mechanical system is completely integrable. And Lux pairs were just found some years before in the study of PDEs, and this is an interesting application how to finite dimensional systems in classical mechanics. So here's the Hamiltonian that appears in Moser's paper. So you have n particles moving on the real line, and they interact with this 1 over x squared two-body interaction. So his idea was to find n, capital N by n complex matrices. Actually, the expression is not so hard to write down. So depending on the position and the momenta, and there's another matrix also depending on the position and momenta, But if you cook up these matrices in the right way, you will see that the equations of motions are in fact equivalent to this Lux-type equation. And then you basically get for free n-conserved quantities, for instance, the n eigenvalues of this n by n matrix or the traces of powers of these matrices. And then you have to check, of course, that these are in involution technically, but this is done in Moser's paper and you are done. So you get a nice kind of way of proving that this forms a completely integrable system, no matter how large this n is. This is an important effect, because previously it was known it's a completely integrable state for n equal to 3, which was some kind of thing, but he found a way of doing this for, so to say, uniforming an n if you wish in some sense. So this was something interesting. A year later, and I mentioned this because it will be relevant for my talk, there's another very interesting explanation of this fact that this is a completely integrable system. You can also represent, so to say, the solution by using another matrix, n by n matrix, which evolves linearly in time. So there's a constant matrix which happens to be Moser's matrix taken at time 0. So you just add in the initial momenta and initial positions. And then there is this matrix M0 which just contains on the diagonal the initial positions. Then you let this matrix linearly flow in time, and you find that the eigenvalues of this matrix are exactly solving the equations of motion of Moser systems. So there's a nice way of solving this problem in some sense. You just take this matrix, take the linear flow, and then there's of course the nonlinear step of calculating the eigenvalues, but nevertheless this is a kind of very explicit way of representing that. I mention this because this kind of expression will also show up in my PDE discussion later on, as we will see. And as you can think, there's a big list of variations on this Calogero-Moser theme, because you can think of what is so specific about 1 over x squared interactions. There are a big class of functional expressions which also somewhat mimic this whole theory, and also you can also think about other settings where you also have some kind of matrix valued variables entering here, which is called typically spin Calogero-Moser system. We have a big family of that. So now comes, of course, the next step to think how to relate this to a partial differential equation. And this is again now a business which you can see at least on a very heuristic formal level by taking some sort of continuum limit. You think of placing these Calogero-Moser particles maybe not on the real line, it's maybe more convenient to do it on a circle with periodic boundary conditions, and trying to take some kind of limit as n tends to infinity. And very formally you can think, okay, my natural variables for this continuum limit is some kind of mass density and a momentum density. And in a formal way, so this was studied by Wigman from University of Chicago, theoretical physicist and collaborators, you can obtain this kind of nonlinear Schrödinger type equation. So why this complex valued field? So in some sense, the modulus of psi corresponds to the modulus squared, to the particle density in some sense, and the argument via this formula to the velocity density, which is the momentum density divided by rho. So it's kind of a Madelung transform. And people talk about Calogero fluids in this setting, but it's a nice word. But one thing which is somewhat interesting is here you see two terms arising. So if you think about the last term, this pure power nonlinearity, and here's a minus, but I have a minus here. So this is a repulsive L2 critical interaction, which somewhat survives this limit. And there's another term which contains this derivative nonlinearity, which scales the same. Also, they are on the same scaling size. And this is more like a focusing self-interaction. So there's maybe a fight between these two nonlinearities. So it's not a clean kind of power type nonlinearity. This is this mixed thing. And then there's a way to get rid of these two terms in some sense by combining them into one, by making a suitable gauge transformation that you also find in this Wittmann paper as well. So what you get, you can somewhat combine these two nonlinearities to one nonlinearity of this type, where you see that the projection onto positive frequencies, the Cauchy-Segal projection, enters naturally. So you take the derivative of minus I times dx is the scalar d, of course, of the mass density, if you wish. Then you project it onto the positive frequencies. There's a 2 here, which is just convenient for us, and times u. So this is somewhat the equation I'm looking at. So this is the nonlinearity I wanted to introduce. This is the Calogero-Moser NLS for us here. So this kind of thing. So the fact that we have positive frequencies entering naturally is also physically considered as a chirality condition. So positive frequencies, just living on the positive frequency is something also rather natural in this physical setting. All right, so I will have this little notation here that just combining d and pi plus, write d plus. Of course, these operations commute, so it doesn't play much of a role in which order I do this, so I can more compactly write this equation like this. Okay, so this is now the Calogero-Moser NLS in a way I like to have it for my talk. So what's the natural scale of Sobolev spaces are, of course, Hardy Sobolev spaces, where we take the intersection of HS with L2 plus. So L2 plus are the L2 functions on R, which have support of the Fourier transform just on the non-negative real line, and as you all know, this can also be seen as a certain class of holomorphic functions living on the upper complex plane. Okay. I just mentioned that this is not completely somewhat isolated to think about certain equations in this kind of chiral form where you use positive frequencies of, for instance, the Benjamin-Ono equation, which has, of course, a real valued field which evolves, but you can, of course, project onto the positive frequencies. You obtain this kind of nonlinear Schrödinger type equation. And you see, of course, here just have quadratic, and here you have cubic. And in some sense, this is kind of the mass-critical sibling of Benjamin-Ono, if you wish, this Calogero-Moser equation. Okay? Something of this form. And then I should mention that this kind of equation already appeared in the literature in the setting of fluid mechanics, was derived by Pilinovsky and Grimshaw. However, there's a switch of signs, which in some sense corresponds. This will be a focusing case because we will see ground states, solitons, and maybe also blow up, at least blow up in infinite time. This is the result I just said in the beginning. This growth of Sobolev norms can also be seen as a blow up in infinite time. And this is a kind of a repulsive case where you don't have any finite energy solitons. But of course, it also is a completely integrable system as well. All right. So let me then discuss so much about the derivation, discuss the features, some main features of this equation, and then come to the results. So here's the equation, just to remind you. First of all, if I have these positive frequency solutions like in this Hardy space, this is of course nicely preserved by this equation, so it makes sense to consider initial data. This Hardy property is preserved, so I'm discussing this equation on HS plus spaces. So the positive frequency is somewhat entering this naturally. Then there is something interesting about it. You will find it's in Hamiltonian PDE. It has a conserved energy, but it's not so easy to really just guess what the energy is. If you naively just take, okay, I'll multiply by u bar and integrate, I get the energy. No, there's this dot, dot, dot. It's a bit frustrating first. This has to do because the symplectic structure is non-trivial, which is behind this kind of thing. But once you find it, and Jalal mentioned this, completing the square is something that appears here magically. You can write the energy as a complete square. It's non-negative, and it can be written like this. So it's du minus this term here. So this is much different from cubic NLS, as we know, where the energy can also be negative. So, for instance, this already tells you I cannot really adapt like a classical theorem for NLS, focusing L2 critical NLS to show that negative energy data blow up at finite time, because the energy is always non-negative. It somehow prevents this simple argument. There's also conservation of L2 mass. It's of course important. And just to show you, the momentum is a bit twisted because of this term. This has to again, that there's this kind of funny symplectic structure hidden in this, so that the generator of translations gives you this conservation option. In fact, you have, as I said, infinitely many conserved quantities, because there's a Lux structure that I will discuss later on a little bit more deeply. And again, we have just mentioned this L2 critical. I can rescale the solution preserving the L2 mass, and this is somewhat indicates that if the L2 mass initially is sufficiently large, I may have a problem, even if I have infinitely many conserved quantities, because this hierarchy somewhat breaks down to give you some kind of good control on the solution. This is an interesting feature of this solution. Yes?
Can you just write for me the transformation you wrote in the very beginning to go from the two-term, you did the gauge transformation. If you just write for me the gauge transformation, if you remember it offhand.
I remember it, but I don't know.
It's behind you, just
The tablet you can write it on.
I write here, okay, so it's like psi, this was my original variable. I take e to the I minus infinity to x, and I take the absolute value squared dy. So y of tx is the solution times this phase factor is my new u of t of x. Okay. I should say this kind of gauge transformation also plays a role in the classical derivative analysis. So it's kind of a magic thing that this also appears here. I have further explanation for this.
And my question was, can you relate energy with any of the conservation law of the discrete system that you had before?
Yes, in a way it is kind of naive continuum limit of the discrete thing when you write down what this Calogero-Moser matrix actually is in some sense. Okay. So one, of course, important class of solutions are, say, you look for ground state solutions, which in this case will be, in fact, stationary solutions. They do not depend on time at all, and they are just the minimizers of the energy functional. Remember, the energy is non-negative, and a minimizer should, so to say, give zero energy. Of course, the zero solution is a trivial minimizer of the energy. I discard it. And because of the completing square trick, the Euler-Lagrange equation for the minimizer is a first order equation, which is nice. But it's of course still non-local because of this Cauchy-Zebo projection. Nevertheless, with some slick tricks, you can somewhat, in fact, prove uniqueness of this solution. Here's an explicit solution, and we can prove that this is up to symmetries, translation, scaling, and trivial phase, the only solution to this problem. So you have a complete classification of the minimizers, and in fact there are no critical points of the energy. So it's a complete classification, so to say, of ground state solutions, or of stationary solutions, in fact, and also of traveling wave solutions, because you can apply a certain Galilei transformation, and you can somewhat completely classify with this result all the traveling solitary waves, which are actually generated by this explicit function R, which is kind of the most simple thing you can think of in Hardy space. It's a rational function, okay, with a pole in the lower half plane. It has this critical mass of 2 pi. The energy is 0, of course. And of course, now it sets kind of the scale. What is small, what is critical, what is supercritical. I mean, I will, of course, be much more interested in this regime, like critical mass or supercritical mass. Here I cannot really control the solution a priori, but I want to get results like global existence or maybe some other properties. And this is the somewhat harmless region, and I expect to have, say, scattering to 0 or something like this, at least for certain data which I may know. Maybe one remark is why 2 pi is 2 pi. This is something which is kind of funny, is because you can relate this equation to the non-local Liouville equation in R, which is kind of a model of the classical Liouville equation in R2, via a certain nonlinear transformation. I mean, here I transform the solution to the solution, but in fact I can transform this equation to the equation. So this is also another way of classifying all the solutions which are known. Of course, by your work with Dalio and Martinazzi, you consider this equation as well. I mean, this is kind of an interesting equation in the toy model of geometry in Q quadrature, just as a remark.
And just 1 second, go back 1 second. I just want to point to the typo there. MR greater than M0 is the same as M0 less than M.
Yes, okay.
Yeah,
Yes, okay, that's a good typo. Okay, I confused here the R and the U0. Thank you. Okay, yes. Here it's quite fine.
Yeah, that's okay.
And it's large and not big. Big. Main results. Just to mention Cauchy problem. So now I want to say a few words about the Cauchy problem. So it is locally well posed when S is bigger than 1/2. How to show this? You can construct smooth solutions, which means bigger than 3/2, I guess, if I remember correctly. You know better using an iteration scheme, but you can lower the index of regularity at least to this range by adapting work of De Moura and Didier Pilot for the defocusing case. But okay, the sign does not play much of a role for local well-posedness, and it involves also a variant of Tau's gauge trick used for the Benjamin equation. So then, of course, if you have subcritical mass for such solutions, it's easy to get a priori control on the energy norm, but also on any higher Sobolev norm, thanks to the Lux structure, in fact, and extend the solutions globally in time. And so you expect them to scatter, and you can at least prove it rigorously if you assume a little bit more like a decay condition, spatial decay condition. But okay. So my main question is, what happens for large solutions satisfying this quality? So there's the first kind of non-trivial result of global well-posedness, in the sense that we show that for critical mass, the solution exists globally in time. So there's, so to say, no finite time blow-up. However, we have no a priori control on the Sobolev norms, or say on the H1 norm. And given what I show later, it's conceivable that you have solutions in this regime which exist for all time. Okay, this is proven here, but which also have Sobolev norms that grow with time. This is something because this is done by an indirect argument to show that the solution exists globally in time. It rests on ruling out minimal mass blow-up solutions. I mean minimal mass blow-up in finite time. So what's the idea? It's a bit a twisted idea. It's like you assume the solution blows up in finite time, having of course this condition initially. And you can adopt the strategy of Merle, who somewhat classified minimal mass blow-up for L2 critical focusing NLS. And you can funnily run this argument to see that eventually such a minimal mass blow-up solution has to be a pseudo-conformal transformation of the energy minimizer, which is this ground state R here. Okay. Also, our equation has this pseudo-conformal symmetry, like the classical L2 critical NLS. However, it's not so compatible with our equation because, for instance, the very slow decay shows that this right-hand side, you conclude the initial datum must be after some transformation of this form, but then the right-hand side cannot be in H1 anymore because if you calculate the L2 norm of the gradient, because of this slow decay, this is plus infinity. So the object that you say is the only way of generating a minimal mass blow-up solution cannot lead to a minimal mass blow-up solution because of this regularity condition here. However, this does generate a blow-up solution of my equation, but with much less Sobolev, just L2 a little bit better than L2. So it's a bit delicate, but if you stay in H1 or higher regularity, you can always extend the solution to all times when you have critical mass. So now I want to enter the regime of supercritical mass. And there's a way of making first a naive ansatz. So I just want to say, okay, I make this pole ansatz. So I take this kind of linear combination of rational functions with one pole. And of course, I have to have these coefficients ak. And I just make the ansatz say just depend on time. And I plug it into the equation itself. Of course, because the d and the p plus play nicely with rational functions, you will see that, okay, a necessary condition that this somewhat is somewhat preserved, this ansatz, is that you get a not so trivial set of nonlinear constraints among the AKs and the ZKs, which you can also check is then preserved by the flow by hand. It's a bit kind of thing. One thing which comes out of these constraints is that the quantization of these solutions, if they exist, the L2 mass of these solutions, if they exist, is always quantized by 2 pi. It's always quantized. It's an outcome of these nonlinear constraints. So this means they must be large data solutions because they are above the ground state, or if n is 1, then it's the ground state solution. This is not very interesting, but if n is bigger than 1, it's. And you find, at least formally, that these poles satisfy the equations of motion of Calogero and Moser. However, with complex positions now living on the lower half plane and not on the real line. And that's this kind of a delicate thing about it. I will come to this. Because there is, now you can say, okay, I'm happy and I just do this ansatz. But the point is these poles can collide. And then, of course, this ansatz is invalidated at this point because you have to take into account collision of poles, maybe. But nevertheless, ut of x is maybe still nice. You have to take into account, say, double poles, which is not so pleasant. I mean, you have to make a more general ansatz. Or possible blow-up. This means like these poles, I know, let me old-fashioned do it like this. So you have the situation, you say have 3 poles, Z1, Z2, Z3. This is the real axis. This is the lower complex plane. And so they can collide. This is maybe something I don't like so much, or one of the poles hits the real axis in finite time. And this is, of course, bad for the high. Then you have blow up of the solution in some higher Sobolev. So how to somewhat deal with this possibility. So the right approach is you use the Lux structure. You want to really get more kind of a general scheme which does not work on this just level of ODEs, but you want to express something which is called a multi-soliton using much more the Lux structure and also study the dynamics. And you don't care so much about collision of poles. Everything is nicely embedded in your formulation. I will come to this. So what's the Lux operator finally? We have seen it on the blackboard already. It is just coming from this, writing it as a complete square. So introduce this operator LU, which is df, and then you project first f on u bar on the positive frequencies, and then again a projection again, multiplying by u again on the positive frequencies. So we're writing it as this iterated projection onto the positive frequencies, and every projection can be written as a triplets operator. Okay, so this is kind of there's a first order derivative, and then there is a triplets part, this double triplets part, if you wish. This is the Lux operator. Of course, you have to find the right b to see that this the equation has this Lux structure. Okay, and now you see you find from this kind of thing that you have a hierarchy of conservation laws by just taking these moments, so to say, u L u to the k applied to u itself gives you there's a k here missing a set of conserved quantities, and I0 is the mass, I1 is the momentum, and I2 is of course the energy, but you can go further and further. So just mention something. So this operator you can show, we show that every eigenvalue is simple, which is not so clear because it's a non-local turbulence part here. You get a general bound on the number of eigenvalues in terms of the L2 mass of this potential U that you enter here, divided by 2 pi. And LU can have embedded eigenvalues, and it's in fact easy to generate embedded eigenvalues, but this bound number applies to this. So also you can control the number of embedded eigenvalues if you wish. So this is a very general bound, and you see, for instance, if L2 has subcritical mass, there is no bound state, which is somewhat, how do you say, compatible with the idea that the solution is just maybe scattering and there's nothing really going on. And just to mention, the Lux operator for Benjamin Ono looks very similar, but there's only a TU part, and we have a TU bar, TU part here. So this also corresponds to cubic and quadratic. So what's now the right maybe setting of what a multisoliton is, not just the simple ansatz I wrote down. It turns out if you study this operator LU, it is a specific class of rational functions, which is of this form. So I confused you something with the P and the Q. The Q has to have degree n, the polynomial, and P at most n minus 1, and there's an algebraic constraint among the P's and Q's. And this is also preserved by the flow, by the way. So you get quantization of L2 mass, and of course when n is equal to 1, you recover R of x up to symmetries. And they all have slow decay. They all have slow decay. So they are slowly decaying guys. And I should also say that if this polynomial has multiple zeros, this corresponds to the situation of pole collision. But I don't care here in this world, this does not play much of a role. And we do have colliding poles, because you can work out, for n is equal to 2, you can work out explicitly everything, and you see also examples where you have 2 poles and they collide at a certain time, and then they go afterwards this collision further. Okay. These multi-soliton potentials turn out to be optimizers of this eigenvalue bound, and also they such a potential only is supported in the pure point spectrum of LU. So you can express U in terms of linear combinations of the eigenfunctions of LU. So this makes this problem now approachable, that this is some kind of thing which takes place only in a finite dimensional world. You have to somewhat now, the right way is to study the time evolution of these eigenfunctions, and you somewhat have to understand how to express the U in terms of the eigenfunctions, and then you have a way of expressing the dynamics. And then you might get somewhat concrete information about the long-time behavior, for instance, of these multi-soliton solutions. And here it is. So you find a way of expressing the evolution of a multi-soliton of any n order in terms of taking the resolvent, M of t will be a matrix, an n by n matrix, which evolves linearly in time, which is somewhat compatible with what you have seen from the 70s paper expressing the Calogero-Moser system. And x and y are certain constant vectors. It's a bit different notation than in the paper, depending on initial datum. So here it is. So you also have this linear evolution of this, but you have to take kind of inverses, which makes it, of course, a bit non-linear basis. So global in time existence now boils down to the question that the eigenvalues of these matrix stay in the lower half plane for any time, which is a question of linear algebra. And you might say, okay, of course there are nice, sufficient and necessary conditions for a matrix to satisfy this, but like Lyapunov, there's a Lyapunov condition. Okay, you can find it. But okay, it doesn't bring you much because I don't know how to see it for this kind of thing to check that. So you have to be kind more into this problem, and of course you have to understand how L0 and M0 are related. Of course they are not freely moving around, and they satisfy a specific commutation relation, as you might think. And if you study this in the right way, you will see for any finite time, you will be able to rule out that M of t, this matrix, has a real eigenvalue, which then corresponds that one of the poles hits the real axis, which would be bad. We would have a blow up in finite time. So we can rule this out, and we get the proof global well-positiveness of the solution for all times. Once you have that, of course, you can then start to say, okay, what happens for large times can be understood by precisely understanding how this matrix behaves when you factor out a t, and then 1 over t becomes a small parameter here, and you have to do a matrix perturbation analysis in terms of this. And then you can get a, so to say, fine description of the solution for large times. One good fact about this is, of course, L0 is related to the Lax operator, and we know the eigenvalues are real and simple. This is very pleasant when you do perturbation analysis. And of course, there's a specific structure, and there's lots of cancellations, so you really have to expand much further than you would naively expect to see effects coming out. But you can do this. And what you then finally get is, of course, this result, that you can extend these multisolitons for every n. For n equal to 1, the first part is, of course, trivial, and the second part is wrong. But for n equal to 2 or bigger, you have global existence for all times of these large solutions, and you have a precise, so to say, rate of blow-up of these infinite type blow-up of these Sobolev norms. It's somewhat related that this is also a bubbling result. So these are kind of bubbles in some sense. In large times, you have a nice bubble, which is, so to say, one of these poles will eventually settle to something finite and nice in the lower half plane. And all the n minus other poles will eventually disperse from each other because these velocities are all different, but they all will asymptotically go to the real axis from below, and this will then generate the growth of the Sobolev norms. Of course, it's much more precise what we can write down, how this behaves. But as a first approximation, you will see that these are kind of solitons which concentrate so extremely in infinite time, like delta functions. Of course, this is much different to other completely integrable PDEs on the line, where the hierarchy somewhat gives you control on all Sobolev norms a priori. For instance, there was a nice recent work on the L2 critical. It's also an L2 critical derivative NLS, which looks like this. Globally well posed, it's now known in L2, and you all get a priori bounds of the solution. This was done recently by Kilek-Vishan and co-workers, and also just before that by Bahuri and Perelman, which instead of L2 maybe H1 half, if I'm not mistaken, no better. Yeah, but of course, these were really breakthrough results on this well-posedness theory for this. And you immediately see, if you think of adapting certain techniques here to get, for us, kind of global well-posedness for large data doesn't seem to be working out in this case. And also this result shows you there is no hierarchy that you can use to control large data in general. I mean, I wrote down a hierarchy, and I can show it does not work, but there could be another hierarchy, but this is definitely showing you cannot find a hierarchy in general for large data solutions. All right, so I'm almost at the end of my talk. I mean, of course, I could maybe tell a little bit more that this is one aspect of these integrable systems that you get from these Calogero-Moser systems. There's another one which we like to study more intensively, which is more geometric, which comes from spin Calogero-Moser system, which is kind of an analog of the Schrödinger maps equation. But I think I like to just say a little word about something. This is kind of following up in the direction, and this is something, this will appear, I think, in Patrick's talk tomorrow. So after we worked on this multi-soliton problem for the Calogero-Moser NLS, Patrick found an explicit solution formula for the Benjamin-Ono equation, which, of course, for the Benjamin-Ono equation, we will explain in great detail what it means tomorrow and how to apply it to something. But in our setting, it also applies that you can get a solution formula, not just for these multi-solitons in terms of resolvents applied to initial data. We will explain what the I plus is. It's not so important. The only connection I want to make is you clearly see that in the more general setting, you have the correspondence that these matrices, which in our multi-soliton case is just, of course, it's a matrix, become operators, so unbounded operators, which evolve linearly in time, if you wish. And but the hard part is that you have to do the resultant calculation and see what you end out of it. And this G, which also plays in this part which I discussed here, a fundamental role, proving, for instance, spectral properties like simplicity of eigenvalues and other things, is the generator of the adjoint Lax-Berling semigroup, which is kind of the central object behind how L talks to G is somewhat fundamental of understanding this formula and many other spectral properties. And then also in the Benjamin-Ono, which has a different Lax operator, this is again very important in the Szego business, Szego equation, it's important. So these equations seem to fall under kind of the same umbrella in some sense, although the Szego equation is called non-dispersive, but that Hardy spaces and this will play an important role seems to be something that needs to be investigated. So thank you very much for your attention.
Thank you very much, Enno, for the nice and interesting talk. So we have time for questions and comments.
At some point you wrote down the whole solution and the whole is coming through the real line. You wrote it as to be in H1, but it's going to blow up in H1.
What is going to
When you reach the
Yes,
axis.
it will
But
reach.
you had bound like t to the 2s. If s is 1, it's like bounded by t squared. I mean, can you
It will
explain
blow
that to
up
me?
in infinite time.
Why not finite? I mean,
Yeah,
why
there's
did
a-
you not reach the boundary in finite time?
Because I
I'm
can.
missing something here.
Yeah. Because I have this formula for this solution for the multi-soliton, and m of t behaves like this. So these are certain matrices, and then I can show that none of the poles will hit the real axis in finite time.
So this is not going to be possible.
Yeah, because you somewhat, okay, this is a proof more or less by contradiction. You assume you have that for some finite time, this matrix m of t has a real eigenvalue. And then you work with this, and you work also using what you know about commutators between L0 and M0, and then you say, oh no, this cannot be possible. Contradiction. However, you will finally see that in infinite time, they are tending to the real axis. I mean, so then you see, so to say, the fine structure finally. Okay, so but you rule this out. Of course, there are the A's. I mean, they're kind of, when I made the ansatz with the residues and the poles, the A's could also blow up in principle, I mean, in amplitude, but this cannot happen. I mean, this will not happen. I mean, this is something. So it's only the poles that dictate whether the solution gets singular or not.
And the relationship between u and psi, I mean, if you know pu, if you know u as you did,
Yeah.
can psi become worse before u becomes? I mean, that's what I'm trying to look at the relationship between them. That's why I asked you to write it.
I think the HS norms are comparable. They are comparable. It's a diffeomorphism in the HS spaces where this nonlinear gauge transformation. So if you can control the HS norm of U, you can control the HS norm of psi and vice versa. This is also something that, because the Kilip-Vijan discussion, they also use this kind of gauge transform with maybe the different sign here, because for the DNLS, And they have kind of the same thing, that they reformulate their equation using such a gauge strength form, and you can somehow compare these norms.
Maybe just an additional comment. You should emphasize that the fact that the poles are going to the real axis is always true, but for n at least 2. Because for n equals 1, you have a soliton.
Yes,
yes, it's very important.
Yeah, here,
So
I said, maybe it was overheard, when n is equal to 1, of course, the first part is true, and the second part is wrong. Okay.
Yes?
So here you have a well-continued result in the supercritical case for multisolitons.
Yes.
But what about any type of initial data? Is there a hope of somehow approximating it by a multisoliton and having some kind of perturbative result?
I don't think so. The multisolitons are also very special. I mean, you have this quantized L2 norm. I mean, I cannot just say, okay, I take large data and I can somehow approximate it by a certain multisoliton with a lot of n's. This is not possible generally. These are very specific solutions. But a good question, or maybe a good question, is to study close to a multisoliton, what you could say. But it seems, I mean, we are starting to understand close to a ground state, but close to a multisoliton, it's kind of difficult. And I should say that the turbulence behavior is somewhat not really expected, in the sense that it is due to a fact that when you do this matrix perturbation analysis, that there's a cancellation trade taking place at an order where you think, you should get a real, a contribution, and it's not there. So it's due to a specific cancellation that you will see this, because normally you would think finally these poles will stay bounded away from the real axis, but this of course not happening.
Yeah, the reason I'm asking is it's a bit reminiscent of the point vortex system for Euler, right? Which you can go both ways in the point vortex solution, the specific solution of Euler, in the limits of which is within the equivalent, I guess, of your soliton. If you take a large number of vortices, then in the limit you get Euler.
Okay.
And on the other hand, you can approximate any solution as a function of the point vortex circuit. So that's why I asked.
Okay, but here,
But maybe it's not the same thing.
I don't see so much.
do you have some kind of quantization?
I don't think so.
I don't think so.
Maybe that's the
It's an important.
Yeah.
But I think in the half-wave maps case it's maybe different, because any rational solution will stay rational. I mean, the multisolitons are huge manifold.
We have more multisolitons in another equation.
I just want to say there's another equation where what you say is maybe possible.
Yes, Daniel?
Shouldn't the size of the eggs be coupled to the imaginary part of the disease, because you want those guys to be really close to multisolitons?
Yes, that's right. I mean, you can see it's coupled through these nonlinear constraints I wrote down, which somewhat, so to say, relate the poles with the residues and so on. But then there's another conservation law, which consists the sum of the residues is. I mean, you can use things to somewhat. I mean, it's not entirely clear that you get this precise formula. You have to work a little bit to understand that you get exactly this infinite time law.
Yes, did you?
So removing the RDB condition.
Yeah.
So would you expect a finite point?
Okay, when I discussed the minimal mass blow-up result, I mean, we rule out the minimal mass blow-up. You can, of course, throw away the Hardy condition. So we also rule out that there's no H1 solution that blows up in finite time, which is more than H1 plus, of course. Whenever you enlarge the space, you might think there's a better possibility that the solution can blow up.
So the minimal mass is ruled out.
The minimal mass is ruled out. I mean, the solution I can write down is a minimal mass blow-up solution, but the regularity is below H1 half. And there we don't have local well-posedness, so you are in a regime where it's not so clear.
Yes, then
One more question. So when you apply this classical conformal transformation, why don't you get out of this space of positive frequency localization?
You get out of the space. Okay, I yes, that is a good point. When we ruled out the manual mass blow up, there it was. Yeah. Here you can already stop if you're just interested in positive frequency and solutions in the Hardy space, because this factor kills the Hardy space property. But I want to go one step further and say I forget about Hardy spaces, but also this very slow decay of R kills the finite energy condition. So this is, yeah. So the pseudo-conformal transform is absolutely not compatible with the Hardy space partition. This is something which also maybe is a good indication that you might have blow up when you leave the Hardy space, but if you stay on the Hardy space, there's maybe no chance to blow up. But we will see. There are claims that there might be blow up.
Okay, then I suggest we thank all the speakers for this morning.